Hey everyone, welcome to the section on Big O notation. Big O notation is a super important topic, and in this section we've got you covered. Here we're going to get into what Big O notation is, how it works, what the most common runtimes are we use when talking about the performance of algorithms, why it's so important, and one of the number one tips you can use for improving the performance of almost any algorithm out there. But let's start by taking a look at what Big O notation is. Big O notation is the language computer scientists use when comparing the performance of algorithms. It's a way of looking at the dominant operations in an algorithm and really comparing it along two axes: time, how fast the algorithm goes, and space, how much memory it takes. Let's take a look at an example. Here's a function called Finding Nemo. And what this function does is it takes an array of strings, loops through the strings, and if it finds an element called Nemo, it prints out found him. Now we could run this algorithm with one element in an array, and if we do, that'll take about, say, 1 millisecond. That's what this code down here is printing out. But watch what happens as we increase the number of elements in the algorithm and run it again. We can see that it starts to take longer. As we increase the order of magnitude of the algorithm, it just keeps taking longer and longer and longer. And in this case, the relationship between the number of elements we're passing in and the number of searches we're doing is linear, meaning it goes up in a straight line as we add more and more elements. In the language of Big O notation, we call this linear time, or O to the n, because there's a linear relationship between the number of elements we're passing in and how long it takes this algorithm to run. That's just one example of a Big O notation runtime characteristic. We have others too. We have ones called constant time. Constant time is when we have a function that doesn't really do any looping or anything complex. It just does calculations and returns as quickly as we can. This time we call O to the 1 or constant time. Very quick, we can't go any faster than that. Linear time is the one we just saw. This is characterized by loops. Whenever we have a for loop and the number of loops is directly proportional to the number of elements we pass in, we call that linear time. One important concept here, however, is to note that we always talk about Big O notation in terms of worst case performance. In other words, if we ran this algorithm and the very first element contained a 0 and we return 0 here, we wouldn't say the performance of this algorithm is O to the 1 because we only looped once. We always need to go and check the worst case, which is why it's still O to the n. So when it comes to Big O notation, we're always looking at the worst case performance. There's also ones with funny, strange sounding names, things like logarithmic time. In this case, whenever we continuously half an element and run it through a loop, the behavior of that is logarithmic. In other words, we're halving the elements each time. And you see this in algorithms like the binary search tree. And then we've got really non-performant characteristics, ones like this one called quadratic. This one, if you've got two for loops, one embedded within the other. This is O to the n, but because it's embedded within another for loop, O to the n, we get O to the n squared, and we call that quadratic. If we look at these in a graph, they start to make more sense. I'm on a website here called Big O Cheat Sheet, and it's really good for just showing the relative comparison of how these runtime characteristics compare to one another. Down here at the bottom in the green, we've got our really fast characteristics. We've got our O to the 1, we've got our O to the log n, even our linear constant runtime of O to the n. These are really good, and these are where we like our algorithms to be. As our algorithms start to perform more poorly, however, we get up into here into some exponential, and here's our quadratic. Here we can see that as we add more and more elements, the performance of our algorithm starts to degrade, in this case in a quadratic manner. Now the reason Big O notation is so important to understand is for two reasons: language and interviews. The language of Big O notation will allow you to compare the relative performance of how different data structures and algorithms do with regards to one another. So it enables you to look at an array, for example, and understand that accessing elements in an array is extremely quick. We call that O to the 1 or constant time. But if we're inserting or deleting elements in an array, well, that's more linear, and that takes a longer time, O to the n. So that language is really, really important. And this isn't just for reading scientific papers or understanding how these things work relatively to each other. It's used in a lot of computer documentation. For example, in Swift, if we go look at how to append an element in an array, we can read the documentation and then see that normally appending an element is very, very quick. It just takes O to the 1. But sometimes, for example, when an array needs to resize itself, it can take longer. And in that case, it's O to the n. Or you can take a look at set. You can go option click, look at the documentation on set, and then see that getting the count from a set is actually really, really quick. It's O to the 1. So big O notation is really important for understanding documentation, how APIs like collections work, but where it's really important for us when it comes to this course is also performing well in interviews. Let's take a look at an example. Here's a super common interview question. Given two arrays, write a function that lets a user know whether one of the two arrays contains any common items. And there's a really simple way of doing this. We can simply take every element in one array, in this case array A, loop through it, then loop through every element in array B, and if we find an element in A that matches B, we can simply return true. Now this is a totally complete correct answer for answering whether or not two arrays have common elements between one another. However, it's very, very slow. This is quadratic in nature. Because we've got this for loop embedded in this for loop, we have something that is O to the n squared or quadratic. It's not the fastest thing on the planet. Let's take a look now at what one of the #1 tips is for improving the performance of your algorithm, and that's using something called a hash map or dictionary. What we can do instead of looping through every element of array A is we can create a hash map or a dictionary and really use that as a lookup table. So we still need to loop through every element of A, which takes O to the n. But once we've got that hash table, when we go loop through B, which is no longer embedded in the for loop of A, we can do a very quick lookup and say, hey, hash table A, if you contain the element B, let me know, and then I'll return true. This is much more performant than the other one because we don't have the quadratic nature of an embedded for loop within another. Here we just have two for loops, which when combined have a runtime characteristic of O to the n. And don't worry, we're going to take a look at how to simplify and determine runtime characteristics in more detail later. But there's really an important concept coming across here that I want to introduce you to now, which we're going to talk about more later, which is that of trading off time for space. In this first example up here, we have something that's very space performant. This function takes no more space than the array elements passed in. So from a space complexity point of view, it's O to the 1. There's nothing going on here. We're not creating any extra structures. Very space efficient, however very slow. What we're doing with the hash table solution is we're trading off space by creating an extra data structure here. We're creating more memory relative to the size of the array we passed in. So from a space complexity point of view, it's O to the n, but we get a big improvement in time or performance. So we're trading off space for time. And that's just an important concept, which is totally acceptable in interviews. You can make this kind of trade-off. And that's why hash tables are one of the go-to data structures we look to when improving the performance of our algorithms. So in summary, what did we learn? We now understand that big O notation is the language used to compare the performance of algorithms in terms of time and space. And four of the most common runtime characteristics we see are constant, linear, quadratic, and logarithmic. We also learned that when it comes to talking about big O, we always need to talk about the worst case performance. In other words, we just don't look at the best case for how an algorithm runs. We always run it to the worst case, and that's the big O notation performance of how that algorithm works. And then thirdly, we also understand that there's also a trade-off between time and space. Often we can improve the performance of an algorithm by taking more space, for example, by creating a hash map, but we gain a lot in terms of time by doing that. And that's why hash maps and dictionaries are one of the #1 ways we can improve the performance of our algorithm is by swapping off that time and space by using them. With that basic understanding of big O now under our belt, let's take this newfound insight and apply it to what is probably the most used data structure in all of computing science today, the humble array.